Okay, so we are in sections 1.6 to 1.7. This is going to be example number 1. We'll try to go through a little quicker through these now that we've kind of just gone through normal stress and shear stress and looked at them individually. So we want to determine the maximum allowable load P, that can be safely supported by the frame when T, okay, thickness, so that's going to be the height right here, that's T, it's 3 inches deep, T is 1.25 inches tall. So if I look at that, that means that cross section is going to be 3 inches by 1.25 inches if we're looking at a normal force that's going straight through. B is 3.5, so that's 3.5 inches. And the wood has a normal stress of 6 KSI failure and a shear failure of 1.5 KSI. Use a factor of safety against failure of 2. So I already know that if I'm looking at my normal stress failure of 6 KSI, then my allowable is going to be 6 KSI divided by 2, which is 3 KSI. And if I'm looking at my shear stress failure, that should say allowable. Allowable. Our shear stress is 1.5 KSI divided by 2, which is 0.2575 KSI. So those are the values I'll actually use. And I know that my normal stress, that allowable, is normal force over area. And I know that that shear stress allowable is shear stress over area. So here I am at the top pushing down. And when I look at this in statics, if I'm pushing down, I'm going to be pushing back up and back up by these two members. And I can also see that they are a two-force member. There's nothing on it but the force at the top and the force at the bottom. So I know that it only has tension or compression, and that it only has, if I were to cut it and look internal, I'm only going to have the normal force. There's not shear and there's not bending moment because it is a two-force member. So purely tension, purely compression, only normal. And it's at 30 degrees. So if we're at 30 degrees here at the bottom, then we're also 30 degrees here at the top, just like that. And 30 degrees, and I have the force of AB, and I have the force of AC, and I can use statics now. I can sum forces in the y direction equals 0, and I'm trying to determine that load P, so we have to call it unknown force P, plus 2 times, because they both are identical, 2 times the y component is sine, so FAB sine 30. And again, I can call it 2 times because they're identical. If this had a different diagonal here, like 35 degrees, then I would have to do a sine of 30 and a sine of 35. But it's identical. So I can now say that 2FAB sine 30 equals, P. And then we can continue working through here that FAB equals P over 2 sine 30, because we have P in terms of FAB and we have FAB now in terms of P. Okay, and we know that this is a normal force, again, because it's a compression member. So if I look at what is sine 30, it is 0.5. 0.5 times 2 is 1. P over 1 is 1. So FAB equals P. Look at that. Pretty easy peasy. Pretty easy peasy. So now I need to actually look at this member. If I look at this member that's coming down, here's this member, and it's in tension. So the internal normal is going to be equal to P, because I already said that the force in AB is a normal force, and by statics we proved it equals P. So I can actually now look at the allowable here. So if my allowable normal force is 3 KSI, and that equals the normal force of AB divided by the area of AB, then I have 3 KSI equals P, because that's normal P, all of it the same. And my cross section is 3 inches times 1.25 inches. And so P equals 3 KSI times, that's kips over inches, times 3 times 1.25. So the maximum force P that I can have with that normal force is 11.25 kips. Okay? So, but what happens down here? What happens down here? If we go back and look down at this joint, what we can see is that we have this notch cut in. Okay, we have this notch cut in, and I have this member coming down into that notch. Okay, I have this member coming down into the notch, which means we have, okay, we have this member coming down at a diagonal. I'm going to have a force that's acting in that direction, and I'm going to have a force that's acting down. Okay, which means if I'm pushing in that direction, I'm going to be developing a shear force that's resisting that in the wood. So if you look, what happens? See how that's in a notch? As I'm pushing in that wide or in the X direction, I could have a shear failure of that wood. It could just split right down the edge. Okay, so here we are pushing, and we're coming in at some force P, and then we're pushing into that direction. And what angle are we coming in? You see we're coming in at 30 degrees. So this X component of my force is going to be, okay, sine, cosine. So cosine 30 equals X over P. So X equals P cosine 30. Okay, then when I look at my free body diagram, I am pushing P cosine 30. I could have a shear failure of that wood, V, so I can now say that that shear is equal to P cosine 30. So if I'm looking at shear stress, which is V over A, I found that I had an allowable shear stress of 0.75 KSI. My shear force is that X component coming in, so P cosine 30, and then my area. So let's go back and look at our area, okay? Look at our area. So this, where it could shear, is 3.5 inches long, and then the thickness of it would be 3 inches. So if you could look at that area, it would basically be, that's what we're looking at, but it would be, you know, down there. So our area is 3.5, 3 inches times 3.5 inches. And when I cross multiply, I get a value of 9.09 kips. Okay. I could also look at bearing. Okay. I could look at, if we're pushing down like this, there's going to be, we could have a bearing failure of that Y component. So P sine 30 over 3 inches deep. But I would need to know, like, I could go back and use geometry and maybe figure out what that is, assuming that we're cut straight up and down. But that's, we weren't given really a lot of information for that, so we're just going to ignore it. So am I going to use the maximum load that I can safely use? Do I use the maximum load or the smallest load, because this is the maximum for shear? If I go beyond 9 kips, then I'm going to have something happen in the shear area that I wasn't counting on. So the maximum load, P max, is 9.09 kips for this system. So when it says maximum load, I'm actually looking at this point for the smallest allowable, and that's 9.09.